Hey guys, because of our time constraints this week and we have an exam next week and we have exam review on Friday, I would like to do Chapter 6 as a video for you. Now, one of my sections, one of you, has not had any Chapter 6 lecture yet. You had just finished Chapter 5. For those of you who did have Chapter 6 lecture today, this will be slightly redundant, but we will go through it anyways. So, if you have this printout in front of you, the notes, please make sure that you have them. I will be going along with the notes in this video. If you do not have a printout of this, you can find it online and you can keep track of it using the PowerPoint that I've posted online. Chapter 6. Solids, liquids, and gases. I have completely crossed that out because I don't like that title, because this whole chapter is really about intermolecular forces, and we'll get to the definition of that in a minute. So, what we think of when we think of states of matter, we think of solids, liquids, and gases, and again, I'm starting kind of up here, states of matter, solids, liquids, and gases. The main difference we think about in solids and liquids and gases is we think about the density differences. We think of solids as occupying a certain amount of space with a lot of stuff in it versus a liquid with the same amount of space but less stuff in it, less dense. We think of a gas as occupying that same amount of space but even less stuff in it. We have a less dense substance when we are talking about gases. So, again, solids, liquids, and gases, we think of the differences in terms of density. So why is it then that we have these three substances that at room temperature and at our Earth's atmospheric pressure, we have salt. Table salt is a solid, while water at room temperature in our Earth's atmosphere is a liquid, while oxygen, that stuff we breathe in, is a gas. Why is it possible for us to have these three substances and their three different states of matter all in one Earth's atmosphere, all at 25 degrees Celsius, our normal temperature? So we have to think then about maybe the interactions that these molecules are having with each other. These molecules might be interacting with each other. Again, water is a liquid. We think of these molecules occupying this space and interacting with each other in a way that makes them a liquid somehow. So we get to the idea then of this thing called intermolecular forces. Intermolecular forces. If we break it down, a force, we think of a force like gravity. Gravity is a force, right? Gravity is something that as the Earth, we are standing on the Earth. I'll even make a little person for you. So, Earth. We have Earth. Person standing on the Earth. We feel the force of gravity pulling down on us. We think of another force, maybe as some other force of attraction, something like when we have a positive and a negative ion, we have a force, an ionic force of attraction. We call that actually an ionic bond. Again, not a real bond because we are not sharing electrons, a bond in the sense that we have an attraction, a force of attraction between two ions. So, intermolecular now. We've talked about force, but what about intermolecular? If you think of your intrapersonal skills or your interpersonal skills, what are those to you? And I think of intrapersonal as in inside of me. I think of interpersonal as being me interacting with someone else. Intra is inside. Inter is with someone else or with other things. Inter is you and something else. So when I talk about intermolecular forces, I'm not talking about the forces that are holding the atoms together inside of a molecule. I'm talking about the forces between two molecules, molecule A and molecule B, or molecule A and another molecule A, or molecule B and another molecule B. So the forces or the interactions between molecules, in between the molecules, not necessarily within the molecules. So, if we're going to think of intermolecular forces, there are four, well, really mainly three types of intermolecular forces. So if I erase these for now, what I have is ionic. The intermolecular force, the ionic force. Now, ionic force, we think of ionic, ion, should be the force between ionic compounds. So if we have an ionic compound, if we have an ionic compound, ionic molecule, the type of force or type of interaction it will have with other ionic compounds or another ionic compound of itself is called an ionic force. Okay, so if we move to the next slide here, ionic forces. Again, ionic bonds are defined as the strongest of the forces. They are an attraction between a positive and a negative charge, an ionic bond. They are the strongest of the intermolecular forces, and they hold matter together in the condensed state. So they are the strongest of the forces that we will discuss. So if you flip the page over, we now go to dipole forces. So the next one we talk about is dipole, or dipole forces. If we think of dipole, we think of the word dipole. Dipole, have we heard of anything that sounds familiar to dipole? Maybe polar, maybe polar. Polar, where do we think of polar? We think of polar with polar molecules. Dipole interactions are between polar covalent molecules. So if we have polar covalent molecules, the main type of interaction they will have with each other is dipole-dipole. Sorry, there's kind of a glare on there. I'll try to fix that. That only helps a little, sorry. All right, so again, dipole-dipole, we have these ionic forces where we had a full positive and a full negative. We now have these dipole forces where if we look at a molecule, let's just say we have this molecule here. C's and H's, C's and H's. I'm going to change one of these H's now to a chlorine. Now, you should recognize at this point that this is a polar molecule where I have electrons hanging out most around chlorine, so I build up a partial negative charge near chlorine, and I build up a partial positive charge on the other side of my molecule. So if I were to draw my molecule now, I would kind of draw it as a little circle, where on one end I've got this partial negative charge, on the other I've got a partial positive charge. Now, because of that separation of charge, I've created a polar molecule. So let's think of what happens if I put one polar molecule and then add another of that same molecule. So how do you think it's going to arrange itself? If I have partial positive here, a partial negative, and again my other molecule, the same molecule here, if I put another one in, how would it align itself to be the most favorable interactions with this guy? Most likely, we would have it arrange itself to be the exact opposite, where I have the partial positive interacting with the partial negative interacting with the partial positive, and that's kind of like we had my ionic compound where it's full positive and full negative, interacting with full positive, full negative, full positive, full negative, and we made sure that the positives were near negatives, negatives near positive, etc. So my dipole interactions are between polar molecules where I have this partial negative, partial positive, to be able to interact with a partial positive and a partial negative. All right, so the next thing on the list then is hydrogen bonds. Again, hydrogen bonds here. So hydrogen bonds are a special type of dipole-dipole interaction. My hydrogen bonds, and again I'm going to use quotations, hydrogen bonds, where I have, first of all, hydrogen bonds occur between polar molecules. Since hydrogen bonding is just a subsection or a subcategory of dipole-dipole interactions, hydrogen bonds are special because they are extra strong dipole-dipole forces. Hydrogen bonds occur when I have specifically a bond NH in my molecule, or OH in my molecule, or FH in my molecule. So, first rule of hydrogen bonding, determining if I even have hydrogen bonds, is it a polar molecule? Is it a polar molecule? It must be polar to do any kind of dipole-dipole forces, and then I have to say, do I have this bond, do I have this bond, and do I have this bond? So if I look at this molecule here, this CH, 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 CCl, is it a polar molecule? If you answered yes, you would be correct. But does it have any of these three bonds present? I see carbon-hydrogen, 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 carbon-chlorine. I do not have any of those three bonds, so the primary intermolecular force between two of these molecules would be just plain old dipole-dipole. But what happens with water? What about water? I have a molecule of water, and we should know at this point that water is a polar molecule where I have a partial positive buildup near my hydrogens, a partial negative buildup near my oxygen. So I know that this is a polar molecule, and therefore I will have dipole-dipole, I'll call it dip-dip, dipole-dipole interactions, but I also will have this extra strong, this super strength hydrogen bond interaction. So I will have both. I will have this hydrogen bond where I have another water molecule come in, where I have this partial positive charge on the bottom and this partial negative charge on top, where I have this nice hydrogen bond again. This hydrogen bond, it's not a real bond because it's not sharing of electrons, it is just an interaction, it is just an attractive force. So, this hydrogen bond, now why is that hydrogen bond so special? Why is it a subcategory of dipole-dipole? The reason for that is if we look at each of these bonds, this NH, OH, and FH, we realize that although the charges are still partial positives near the hydrogens and partial negatives near the fluorine, oxygen, or nitrogen, again, because of differences in electronegativity, we realize that this is not a normal partial negative and partial positive. This is going to be a really large partial negative and really large partial positive because the electronegativity of hydrogen, or hydrogen's desire for electrons, is really low compared to the other nonmetals, while nitrogen, oxygen, and fluorine have really high electronegativities or really high or great desire for electrons. Because of that, we have a very large partial negative and a very large partial positive charge. So, if we think about this now, we can look and say, okay, well, what is the strength then? We talked about the strength in the ionic thing. It said, ionic bonds are the strongest of the forces that hold matter in the condensed state. Okay, that's thrilling, but what about that in comparison to a dipole-dipole force or hydrogen bonding force? Now, if we look, this is a full positive and a full negative. And these are partial positives and partial negatives. These are partial positive, partial negative, but even bigger. So I'm going to propose a question to you. In my ionic compound, I must have a positive and a negative charge, but what if I have a 2 positive and a 2 negative? What do you think about the strengths of those two ionic bonds? If I have a +1 on this hand, a -1, and they go together, how difficult would it be for you to rip these apart compared to a +2 and a -2? Which one do you think would be more difficult to pull apart? This or this? You should have said this would be more difficult. So again, I see that if I increase the charges, I actually have a stronger ionic pull or ionic force in between them. So if I have a stronger force or stronger attractive force between 2 plus and 2 minus than I have for a +1 and a -1, what about looking at the partials, the partial charges? This would have the strongest, this one would have the next strongest, but out of these two, where I have a big gigantic partial negative, big gigantic partial positive versus kind of smaller partial negative and partial positive, you should be thinking at this point, well, okay, so I have really great intermolecular forces, pretty great intermolecular forces, next best intermolecular forces, where this is almost, because of the differences in electronegativity, it is almost the same as an ionic compound. Again, it is still not full charges, but it's getting closer, versus my partial charges here. So, again, to reiterate, I have ionic forces between ionic compounds, and the strength of those ionic forces is going to get bigger and bigger as my charges get bigger and bigger, because the force depends on that strength of attraction. I have dipole-dipole forces for polar molecules, between polar molecules. So again, I can have this molecule here that has a partial positive on one side and a partial negative on the other side. It will attract another molecule that is polar, that has a partial negative lined up to interact with the partial positive, and my partial positive to interact with another partial negative from somewhere else. So, my hydrogen bonds are a special subsection of my dipole-dipole, where if I have a polar molecule, and specifically this bond or this bond or this bond present, I can say that it will do dipole-dipole interactions because it's polar, as well as hydrogen bond forces. So again, water. Water is, first of all, a polar molecule, so it will have dipole-dipole, again I'll call it dip-dip, dipole-dipole interactions, but because we have this OH bond, that's one of my possibilities for hydrogen bonds, so I can say that this will also hydrogen bond. And those would be the two intermolecular forces that I would find between two molecules of water. All right, so let's move on from that. So we've been talking now about ionic compounds, polar covalent molecules, and hydrogen bonding again must be for polar covalent, but what is there? We've got ionic, polar covalent, and you should be thinking of non-polar covalent. So what about the non-polar covalent? Non-polar covalent, I'm going to erase the hydrogen bonding. Non-polar covalent. Do we have a separation of charge in non-polar covalent? If I have a non-polar covalent molecule, let's start with oxygen, O2, where I have my Lewis structure drawn. You should be thinking, okay, these are two nonmetals. That means I have a covalent molecule. If I have a covalent molecule, I'd have to check for polarity by saying, okay, do I have any separation of charge? Will this oxygen grab electrons more than this oxygen? You should be saying no at this point, and so we therefore say that this is a non-polar covalent molecule. Non-polar covalent molecule. So we have a non-polar covalent molecule. That means that we don't have a slight negative, slight positive. We don't have any separation of charge. So what we should be thinking then is, what's left? On my little list of intermolecular forces, it listed in the front, ionic, hydrogen bonds, dipole-dipole, and dispersion. The last one we have is called dispersion. Sorry for changing up the color on you. Dispersion forces. I have dispersion forces, and those are between non-polar covalent molecules, like oxygen, O2. Now, when we think of the strengths of these intermolecular forces, we think of ionic, again, as being the strongest. We think of dipole-dipole and hydrogen bonding. Again, hydrogen bonding is stronger than your average dipole-dipole, but we kind of consider them in the same subsection. So ionic is the greatest, dipole-dipole is the second greatest, and dispersion would be the least great in terms of strength of the force there. And the reason for that is if we think of a nonpolar molecule, such as oxygen, O2, again, nonpolar molecule, a nonpolar molecule, we think that we don't have a separation of charge. So I'm going to just put this as a bubble here. I'm going to have oxygen work like a bubble. So this oxygen walks into a bar and sees that oxygen, and they know that they have to interact with each other at some point. They got to interact. So what we had here, the whole purpose that we had, all of these characters staying together, is because of these charges, or these partial charges. So what this oxygen molecule will do is he will take his electrons and he will shove them to one side. Now, we should know that when we shove electrons to one side, we create a buildup of negative charge. That means that on the bottom here, we've got a buildup of positive charge. Now, this molecule sees what this one is doing, and he says, okay, let's do this. So he shoves his electrons to the top, where he builds up a slight negative charge to interact with this slight positive charge, and he builds up a slight positive charge on the bottom as well, and we have this thing called an induced dipole, where I induce it, I force myself to have a dipole. Again, when I think of a dipole, my dipole is just the pull of electrons. This little arrow that I draw, this little arrow that points kind of towards my electrons, I induce a dipole. I induce this separation of charge. So, again, in terms of strength of your intermolecular forces, sorry, I'll try to put that in there, we have ionic being the strongest. We have my hydrogen bondings being the second strongest, and that's, again, just a subsection of dipole-dipole, which is the next strongest. And then at the very end, we have dispersion. Now, the one note about dispersion forces is that if we have a big, gigantic molecule, we have a lot of electrons that we can move around the molecule. So let's just say that instead of oxygen, I have something like C6H14. So we should be thinking, well, wait a second, that's a big, gigantic molecule. How am I supposed to know if that's polar or not? And we should look at this and say, in C6H14, what are my possible bonds that I could have in that molecule? My possible bonds are C bonded to H, carbon bonded to carbon, and if we had hydrogen bonded to hydrogen, we'd have hydrogen gas and it would float away. So we know that can't possibly be there. We know that these two bonds are nonpolar. Carbon-carbon, one nonmetal to the same nonmetal, is a nonpolar bond. Carbon-hydrogen is our one weird exception where we have one nonmetal with another nonmetal, but in this case, their difference in electronegativity is so small, we consider that to be a nonpolar bond. So if we have no polar bonds, our overall molecule should be nonpolar. So this is compared to oxygen, this is a pretty large nonpolar molecule where I have, instead of these little blurbs that I have for oxygen, I can have this long molecule here and this long molecule here with quite a few more electrons than just O2. So what I can do then is I can shove all of my electrons up to the top, and I've got a lot more, meaning I can build up slightly more negative charge than I could with oxygen. Again, with this molecule, I can build up slightly more negative charge, slightly bigger positive charge, which actually makes this interaction quite large, or quite great, I should say. So, again, on a usual day, ionic forces will always, well, on a usual day, ionic forces will be greater, stronger than dipole-dipole, and usually hydrogen bond is greater than the average dipole, versus dispersion forces will be the least strong, except when you have a gigantic molecule, maybe something like C40H82. Something gigantic. We would have a lot of dispersion forces, and therefore we would have a pretty strong interaction holding these two molecules together. So let's move on from that then. At this point, we should be thinking, what does this have to do with what I showed you in the very beginning, the salt and the water and the oxygen? So if we look at this, we look at salt and water and oxygen. Again, salt, NaCl. We think of salt as what kind of compound? We should be thinking sodium is a metal, chlorine is a non-metal. I should be thinking of this as ionic. I know that salt is an ionic compound. It is also a solid. Okay, water, H2O. Water, H2O was, okay, so I see a nonmetal, and hydrogen is considered a nonmetal, so I know that this is a covalent molecule, specifically, though, a polar covalent molecule, and it is a liquid at room temperature. Meanwhile, oxygen, O2, we know is a gas. We know that this is two nonmetals, the same nonmetal, so this is a covalent molecule, covalent compound. It is also nonpolar because it is one nonmetal attached to the same nonmetal. They have the same affinity for electrons. So now, with what we've learned about these different forces, what kind of forces are interacting with one molecule of salt and another molecule? When I put them together, I should have, because it's an ionic compound, I should have ionic forces. Ionic forces. Water is a polar covalent molecule. So first of all, it's polar, so I know I'll have dipole-dipole, dipole-dipole, okay? But I also have, I know that water has an OH bond, so I know that it's also going to have hydrogen bonding. All right, oxygen is a nonpolar covalent molecule, so I know the only interaction that I could have, the only type of intermolecular force I can have is dispersion. So now, thinking about that, if we go through, how do we break these intermolecular forces? When we think of breaking, let's just say we think of pulling apart one water molecule. It's one water molecule away from another. When they're this close, when two water molecules are this close, we probably think of them as being in the solid phase. So how do I break them apart? As in make them occupy more space. Now, who occupies more space as a water? If we're in the solid form, how would we occupy more space? We should be thinking, okay, same two molecules occupying more space, a liquid. A liquid would occupy more space. So how do I get water from a solid to a liquid? How do I break those intermolecular forces? And you should be thinking, how do I take an ice cube out of the fridge? How does it increasing the temperature. So to break intermolecular forces, did a little silly picture for you. We do not use a hammer to break intermolecular forces. We use heat. We use heat to break to break intermolecular forces to pull these molecules apart. So now that we're thinking about that, we're using heat. Everything, all of these three substances are in their states of matter as a solid, liquid, and gas at room temperature. So we've given them all the same amount of heat. So why are they at different phases? They're at different phases with the same amount of heat. So again, going back to chapter 1, we think of melting point and boiling point and condensation, freezing, etc., etc., etc. What does that have to do with intermolecular forces? And again, we are breaking intermolecular forces when we add heat. We have to put heat in so that we can break these forces apart. Not breaking bonds, except for the occasional hydrogen bond, ionic bond, again, not real bonds, just attraction or attractive forces. So melting point, boiling point, freezing point, etc., we reach those by either adding heat or removing heat. And we have our physical changes that come about from that. So now, big question of the day. Why does water's boiling point, so I'm going to write this up here. The big question of the day is why does water boil at 100 degrees Celsius? 100 degrees Celsius is the boiling point. Okay? And then hexane, again, this I had it drawn over here before, but hexane, so C6H14, boils at 69 degrees Celsius. Why do we have these two substances having different boiling points? Why do they have different boiling points? And again, the boiling point is the point at which we've reached enough heat to turn the substance from a liquid and turn it into a gas. So water has a higher boiling point than hexane. Hexane boils at 69 degrees Celsius, so we only have to get up to 69 degrees Celsius to boil hexane. Meanwhile, we have to go even higher, 100 degrees Celsius, to boil water. So if we think about it, again, boiling, we have to break the intermolecular forces that are keeping those two molecules in the liquid state, as in keeping them closer together. So if water boils at a higher temperature, that must mean that water, the forces that are holding these two molecules of water must be stronger than the forces that are holding together hexane, two molecules of hexane. And if we go back and look for reasoning on that, what kind of forces are holding water together? Should be, okay, water is a polar covalent molecule, so I know that it has dipole-dipole, again, I'll call it dip-dip, dipole-dipole interactions, and I know the structure of water, so I know that it has an OH bond, so specifically it will have hydrogen bonding as well, okay, and then what kind of intermolecular forces does hexane have? Again, we have this weird thing where I don't want to draw the whole thing out, so I'm just going to think about what I actually have in there. The only bonds that I could possibly make are carbon-hydrogen or carbon-carbon. Again, no polar bonds. Therefore, my molecule is nonpolar. So if it's nonpolar, the only interaction that I can have, the only intermolecular force I can have is dispersion. Now, how do I use these intermolecular forces to describe or explain why I have such a difference in my boiling point? And if we think about it, what kind of differences do we have in these intermolecular forces? Again, dispersion was, if we look back on our list of who has the strongest intermolecular forces or what the strongest intermolecular forces are, we see ionic, again, is the strongest. Hydrogen bonds and dipole-dipole are kind of in the middle, and we have dispersion as dead last. So we think of dispersion here would have the least strong, so the weakest intermolecular forces, as in the weakest force holding hexane and hexane together. Meanwhile, water has one of the strongest dipole-dipole and hydrogen bonds holding it together. So we think, okay, if I want to pull apart water molecules, two water molecules, I'm going to have to put a lot more heat in to break those intermolecular forces. Meanwhile, hexane, two molecules of hexane, aren't being held together very strongly, so I don't have to put that much heat in to separate them. So that's the reason why we have differing boiling points for hexane and water. So let us move on from that. All right, so now going back to chapter 5, we talked about solutions. So when we talk about solutions, we think of things like salt water. Now, we think of salt as being really dissolvable in water, right? We think of salt, we can easily dissolve it in water. Why is that? And does everything work like that? Does everything dissolve nicely in everything else? Or do we sometimes see substances that don't like to dissolve in each other or mix well together? So I'll give some examples. Let's do, so salt, if I can spell it, and water, maybe vinegar, and, well, yeah, vinegar and water, I guess we'll try it. Vinegar and water. What about oil and water? Now, you have all these substances at home, so if you're watching this at home, you could potentially do all these and try it yourself right now. So, salt and water, see if they mix nicely. Vinegar and water, oil and water. What about soap? Soap and water. Now, you wash your hands with soap, and the soap seems to come off with water. And if the soap comes off with water, it must be mixing with water. So, okay, what about now soap and oil? Soap and oil. We wouldn't, I mean, when we think of oil, we think of grease and oil. So if we use soap to clean off grease and oil, it must mean that oil and soap mix nicely. So let's go through this then. We know that salt and water mix nicely. Okay, vinegar and water, you can test that, but I can tell you vinegar and water will mix nicely together. Okay, oil and water do not mix, and we have actually, you should have seen this before in your life, where we actually have, when we add oil and water, we see two different layers. We see our oil on top, and we see our water stick to the bottom. So we know that they don't like to mix nicely with each other. They separate. They do not like each other. Soap and water, we say, mix nicely. Soap and oil, we say mix nicely. So why is it that we have these nice mixings happening? And what we have to think of and what we have to consider always is the idea of like dissolves like. So, when I say like dissolves like, I mean polar molecules like polar molecules. So polar molecules will dissolve or will mix with nicely with polar molecules. Non-polar molecules will not mix nicely with non-polar molecules, and ionic compounds or ionic molecules will interact nicely or mix nicely with other ionic molecules. Now, if we think about it, what is salt? We know salt is sodium chloride. Sodium chloride, water we know is H2O. So if we think of the type of molecules we have, NaCl is ionic, and water is a polar covalent. So polar covalent, but I just said that polar likes polar, ionic likes ionic, and nonpolar likes nonpolar. And if we think about that, it doesn't make sense that salt and water would mix together. So why do salt and water mix nicely together if they are not alike? If we think about it, that's my representation of salt. Meanwhile, water looks like that. We have partial positives and partial negatives on my water. We have full positive and full negative on my ionic compound. So again, if I've got my partial, I'll actually switch these around so that you can see it. If I have my partial positive and my partial negative, I've got this nice little interaction between my partial positive of water and my full negative from chlorine. I have this nice interaction, so I actually do see that ionic will interact with polar molecules. So really, like dissolves, sorta like. Now, nonpolar molecules, again, something like oxygen or nitrogen gas or hydrogen gas or methane, CH4, where I have no polar bonds and therefore a non-polar molecule, will not interact nicely with polar or ionic molecules because they don't have a dipole. They don't have partial charges or full charges at all. So, again, salt and water will mix because I've got this full positive negative charge interacting with a partial positive and partial negative charge, and it works out nicely. Vinegar and water. So we know what water is. H2O is water. What kind of molecule must vinegar be then? What kind of molecule would vinegar be? We know water is polar. Water is polar. Do you think vinegar is ionic? Vinegar maybe ionic, because we know that vinegar and water mix. So vinegar must either be a polar molecule or it must be ionic. Again, if these two mixed, that means that vinegar would not be nonpolar. So what about oil and water? We know that water, again, is H2O. We know that it's a polar molecule. We know that it would mix with polar or ionic molecules. It does not mix with oil. So if we think about it, oil cannot be ionic. It cannot be polar. Oil must be a non-polar molecule. A non-polar molecule. So again, because oil is nonpolar and water is polar, we know that they will not mix because they are not alike. Okay, so just as an FYI type of thing, oils are actually made of these long chains of hydrocarbons, where I have hydrogen attached to carbon, attached to carbon, attached to some hydrogens, etc., 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 where I just have these long chains of carbons and hydrogens. Now this is a very small version of an oil or a fat or greasy substance, where I have carbon, 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 a bunch of hydrogens all around it, and that's kind of the basic gist of an oil or a fat or grease. So in this, again, you can see that all I have are carbon-hydrogen bonds or carbon-carbon bonds. And again, neither of those are considered polar, so this whole molecule has no polar bonds and is therefore a non-polar molecule. So, non-polar molecule would not interact nicely with water. Now, here's the weird part. So, all of that aside, I'm going to erase this. All of that aside, what about soap? Soap seems to have this weirdness where it interacts with water and it mixes with oil. So again, water, we know, is a polar molecule. It's polar. And from the previous knowledge, we know that oil, whatever it might be, is, non-polar. Is a non-polar molecule because we know that it didn't mix with water. So what about soap then? To interact with water, soap must either be polar or ionic. Okay, but it mixes with oil, meaning soap must be non-polar or not polar and not ionic. So if we think about that, how is that possible? We know that soap, we use soap to clean. We use soap to clean either in water or clean off grease, so it must be mixable with both water and oil. Water and oil. So the fun part about soap is that soap is actually both. Soap is made of these long tails, and for those of you who are in biology of some sort, you should recognize this. We call this a non-polar tail. Non-polar tail, again, because it's a bunch of hydrocarbons, hydrocarbons being hydrogen and carbon. We have this end that you should be thinking, okay, that looks non-polar to me. That looks pretty non-polar, so this will all interact with oil. So that's how you get oil to mix in, but now, at the very end of soap, I have this ionic piece where I have something. Now, this is one example. Again, soap has many different examples of this. This is a phosphate group at the end. I have an ionic end that interacts with water. So this is an example of what soap would look like. This is not one soap or any soap. This is just an example where I have a non-polar end, oil, non-polar end, and I have an ionic end, an ionic or a non-polar end that will interact with my water. So it's kind of cool, actually, how soap works. What we have is, I'm going to erase this, hopefully you guys have written this down. What we actually have, when I mix soap, water, and oil, what I get is I get these weird little bubbles of trapped grease. So I have oil in the middle, oily, greasy, non-polar molecules in the middle, and that hydrocarbon tail that has a bunch of carbons and hydrogens, I'm just going to draw it as little squiggles. Little squiggles of all of those non-polar tails, all of those carbons and hydrogens, all those non-polar tails interacting with the oil and trapping the oil in a little bubble. Meanwhile, these groups out here, I'll call it my negatively charged, my ionic ends of my soap, are interacting with water. So when I'm washing a pan with soap, what I'm doing is I rinse with water, I put some soap in there, the soap traps my grease or oil or non-polar whatever in the center, and my water molecules, my waters, are all interacting with the outside of this bubble. interacting, which allows it to be swept away, and the oil and grease and whatever is now off my pan. So soap is pretty cool like that, so that's kind of a big deal. So if we go now to the last questions on here, again, going back, it asks, first of all, why do oils and water not mix? Again, oil we know is nonpolar, water is polar. Do oil and hexane mix? Now this is a big question. Do oil and hexane mix? Again, oils are super nonpolar. We know that oils are just long chains of nonpolar things. So oils, we know, are nonpolar. Does it mix with hexane? Again, hexane was that C6H14. Now, hexane, is this a polar molecule? Non-polar molecule, nonpolar. Will they mix? If I put them together, absolutely. They should mix because like dissolves like. All right. What about water and hexane? So, water and hexane. Again, water is a polar molecule, we know that. Polar and nonpolar will not mix. X on those two. Okay. What about water and methanol? Now, for those of you who have taken a look at the practice exam, methanol is CH4O. Methanol. If I draw methanol, I should draw the Lewis structure first. Again, that's what I need before I do anything about polarity. I have a carbon and some hydrogens and oxygen and hydrogen. And I'm going to do this quickly. You guys should be able to do this on your own. I have methanol. Now we think of this, and I have to consider, for polarity's sake, I have to consider my shape. I have this carbon, which has 1, 2, 3, 4 groups around it, so I know this is a tetrahedral carbon. Oxygen, hydrogen, hydrogen, and hydrogen. If I look at this oxygen as a secondary central atom, I know that this oxygen has 1, 2, 3, 4 groups around it, so it is also tetrahedral, where I have a molecular geometry of bent. I should see that. So overall, is this a polar molecule? And this is a big question to consider. Do I have any polar bonds? Is carbon, hydrogen, carbon, hydrogen, carbon, hydrogen? Those are all nonpolar bonds, but what about carbon, oxygen? Carbon, oxygen is a polar bond where I have pull towards the oxygen. What about oxygen, hydrogen? Is that a polar bond? Should be thinking yes, where I have electrons being pulled towards oxygen. So overall, I've basically got this buildup of electrons over here. So I build up a partial negative charge, and all over here I build up a partial positive, making this a polar molecule. A polar molecule. Methanol is a polar molecule. So what was water again? H2O is also a polar molecule. A polar molecule and a polar molecule should mix nicely. All right. So the last slide on here is basically showing you the solution or the dissolving of ionic compounds in water. And again, that's dipole-dipole interactions or hydrogen bonding interactions interacting with ionic compounds. So with that in mind, that is chapter 6. If you have any questions, please let me know. Hopefully this works out nicely. I hope the video flips and it's not backwards. And again, let me know if you have any questions.